Yes.
So we have been developing over the years already quite some time an iSphere software, which is meant for data management of crystallography data so far. And within this project, we have a team from Oulu, Weizmann Institute of Science, Diamond Light Source, which was originally also developing the software. Now we have support to test the software and so on. And then we have Tommi Nyrönen from CSC IT Center for Science, which is an Elixir site, and we are hosting now the cloud environment at the CSC. So the project, as a summary, the goals of the project is to improve the tracking of the samples and sample preparation, and then we have implemented hands-off sample shipment to other research infrastructures. So this has been the kind of the goal, to track that what was actually done to the sample. We have records usually that how the sample was prepared, but then you have to pick up the sample, do some practical things with the sample treatments, and then you ship it to another facility. And we want to keep track of that whole process and make it fluent for the researchers to track this process. And this is implemented already. And additionally, we want to communicate with other research infrastructures and the databases and what sample information and experimental information they have. In this case, it's synchrotron facilities where we collect the data either on site or remotely or automated data collection and so on. We want to build this link that the sample information metadata is transferred back and forth, not essentially copied, but made accessible through links to different databases and so on. Some of the data is actually copied, but the critical ones only. So the aim was to make now iSphere to the cloud version, make it easier to implement. Previously, it has been hosted on Linux servers or on site. And the requirement is that the iSphere also communicates with the automated crystal imaging systems that are in the facilities. So there has to be a connection to the hardware at the laboratories or facilities, and then to the iSphere software, which is used then by the researchers anywhere, at home or at the office, and to monitor the experiments, make notes, and so on. So the goal was to provide also an easy management of the databases by centralizing this setup so that it's all in the cloud. And this cloud environment would also allow us then to build on top of that different features, because we have a lot of data coming from the users, manually scoring and the experiments and so on, to enable tools to facilitate the actual work done in the laboratory by building this automated drop scoring and so on. That is still to be implemented, I think, but we have some plans towards that now. But this is what the cloud environment actually would enable us to do. So we had a kind of a divided tasks how to carry this out. So it's quite practical things, implementing the iSphere to the CPOTA, we call it Icebox, and at the University of Oulu, and establish this communication and backup protocols, because we have these databases running the hardware at the laboratories. So how to build that communication fluent and so on, and then have also the backup procedure somewhat in place at least. And then we wanted to test this communication with the synchrotrons and recovery and backup procedures, so that if we host other people's data on the cloud server, then how do we carry this out? And the communication with synchrotrons has been implemented quite a lot during the project time. So we have had collaborations with other synchrotrons and ISPIP developers also. So then we wanted to establish this also for other facilities when we have the production server at Oulu, and also within Instruct Eric facilities. And we were at the time writing the proposal, we thought about developing some sort of a fee structure covering the hosting cost, but that has not been relevant so far through the EOSC-LIFE and CSC help. So we wanted also to have a proof of concept, at least for some sort of an authentication system in iceberg, and due to various things that's still under discussion, and then possibly explore this machine learning to help the users. Now we have only one production server at the CSC, so now we are trying to tackle that last task. So we are not exactly where we wanted to be within the project, but of course this are a bit exploratory, the last task, but cloudification kind of enables us to do this. So we implemented iceberg to Sipota at the University of Oulu, where we are located, tested the communication board protocols, have the recovery and backup protocols established, so that actually now there's also copy transfer to the University of Oulu archives. And our production server went to the cloud environment, and we didn't hear anything from the users. So apparently it's working very smoothly because nobody complains, and that's a good sign. And then we have implemented shipment modules to the synchrotrons during the project time, to ESRF, but especially to Max 4, where we previously had this working at Diamond, which uses a different kind of a protocol API. And with Max 4, we have actually built quite a lot of together with them, so that there's actually information and links from iceberg going to the iSpy at the synchrotron, so that the users can access the data easily when carrying out the experiment. And we have also already set up cloud servers to transfer the iceberg instances within Finland and within also Weizmann Institute to now put that cloud environment to real use. There's some complications there naturally, because there's some ancient, not ancient, but not very modern imaging systems and different databases running those and different structures. So we have to make a bit prioritization that where to put the resources and not to develop anything for the obsolete instruments and so on. So we have now centralized basically maintenance of these iceberg instances, and I think that's a clear benefit, because then we can run updates and also backups of these instances from one particular point. And we need an uploader to the home lab to upload the metadata and also the crystal images to the cloud version, but it's also still possible to put an offline version of the server, of course. And this was developed, this uploader, based on the kickoff meeting of this EOSC-LIFE project, and that is why we shifted gears through these meetings a bit, and that is also why we then didn't maybe go as far as we thought initially, but I still think this is the way to go. It's much better not to have these problems with VPN systems and so on. So that was clear benefit from these meetings. And shipment module, of course, helps tracking the sample metadata, and we also have links possible to raw data and metadata and publishing process data. We link to PDB and Proteopedia and so on to these sort of resources from iceberg. And looking at how this would impact the EOSC-LIFE, so looking just at the mission of EOSC-LIFE is to make resources, to provide fair data policies and publish the data and integration of this different research infrastructure and structure repositories, and this is exactly what we are doing basically with this. Of course, it's a very practical example of this resource, but facilitating and helping researchers to access and publish research metadata and raw experimental data. I think that's the key practical benefit for everybody using this software. And we also integrate with databases used in multiple synchrotrons now in Europe. And so, as I mentioned, this kickoff meeting helped to redesign the process, which caused some delays, but it was, in the end, I think, the best way to go about. So that was clear benefit. And now the cloudification allows these further developments, and we have been discussed this with the teams, but have not yet advanced really to these aspects. We have have now initiated some discussions also at the University of Oulu and initiating a project towards this machine learning and implementing at least the first proof of concept for that. Sustainability. So these are the future works I already mentioned. Sustainability is of course supported by Biocenter Oulu, which is the overall allowing us to develop this, but we also secured some funding from the national funding source to cover the development in the coming years. And in addition to the partners, then we of course have to acknowledge the support from the National Infrastructure and Academy of Finland funding our activities. It was partially, and then Biocenter Oulu and University of Oulu of covering most of the things. Also the collaborators in the project, Weizmann Institute, Diamond Light Source, CSC, but also ESRF and Max4, where we have now implemented the metadata transfer automatically with the shipping model. Now I give the word to Ed Daniel to run a quick demo of the system.
Okay, I must apologize. We had the builders downstairs for 2 weeks and they've been silent as a grave. And then literally during Lari's talk, they have started drilling into the walls. So I will do my best to shield you from that noise. Okay, can you see my screen now?
I can.
Okay, fantastic. So I was going to do a live demo, but without a live synchrotron data collection in the middle, it won't work. So here you can see one of the typical plates in our Formulatrix rockmaker systems. This is in our home lab. So the problem is, how do we get that out to our cloud installation of IceBear? So we wrote a PowerShell script, which runs every 5 minutes. That's installed on the Formulatrix database server. And that pushes the images and the plate metadata out to our IceBear installation at CSC running in the CPOLTA cloud. Here we can see the result of that. This is IceBear, the drop viewer. We can see our one of the images that we've pulled across here. We can mark crystals on that image for onward processing, and we can add metadata to that if we want. Each crystal we mark get its own IceBear page, and we'll see more of that later. We then move into the crystal fishing process. Our interface allows us to assemble a shipment here with the minimum of interaction. It's literally a single drag drop operation. Drop the crystal onto the pin, and then the pin gets put into the puck, and then you assemble the puck into the dewar. It's possible to do a lot of this assembly while you're actually creating the shipment. The line between fishing and assembling a shipment is actually quite blurred. But anyway, here we've assembled a complete dewar with a puck in it with our 2 crystals. So let's ship it. Quick check here to make sure that the contents are what we would expect. And as mentioned, you can still scan in a new pin or an entire pack at this point to add to the shipment. So having specified where it's going, we then authenticate with our Synchrotron IceBear credentials. We gather some basic information like proposal, lab contact, safety level, etc. And then there's a final review before we hit the send shipment button. And at this point, we do a lot of pre-flight validation to minimize the chance of a failure halfway through, because unfortunately at the moment there's no way to roll back and delete an item.
You are muted.
Yes, there's no way to delete an IceBear shipment once it's started. Sorry, the builders decided to drill into the wall again. Using the IceBear API, having done the pre-flight validation, iSphere then creates the shipment in ICE-by-B, adding the containers, adding the samples, and then within iSphere we store the ICE-by-B URLs for later use. So there we have it. The shipment worked. And we have a link to the shipment in ICE-by-B, and we can retrieve the metadata for the data sets later on. Just to prove that it works, there it is in ICE-by-B. We still need to manually print off the shipping labels, etc., but all the crystal data has been transferred. So here's the dedicated iSphere page for one of our crystals. You can see that we're able to attach a PDB code to that crystal at a later date. And on the data sets tab, we can see an example of a data set that's been associated with the crystal. And that's done automatically when we press that retrieve data set button. Yes. And opening the dataset metadata, we see the location of the raw data, we see the description and the beamline, including the detector details, and all of that is populated by information supplied by ICE-by-B. We can also associate the dataset with a given PDB code. So we've managed to push the crystallization drop images from our home lab to an iSphere installation in the cloud at CSC, select crystals, assemble and send a virtual shipment, and retrieve information about the collected data sets, all using the ICE-by-B APIs. And finally, we've associated a PDB code, given a complete chain of custody from crystal drop right through to the PDB code. And I'll mute my mic now, thank you.
So that's the end of the?
Yeah, I think there was some grilling. Yeah. So
I think it illustrates the working from home that we've all been doing for some time. So that was very nice. We don't have any sort of questions in the chat, but I do have a kind of question about how many organizations or sites you think could be thinking about implementing this beyond the sort of test cases that you've had so far.
Well, that is kind of what we have to discuss also with the CSC and policies, because the CSC is essentially also funded by the universities in Finland. So within Finland, there's no problem, I think, and then that's why I mentioned this fee policy, because it's a bit open that how do we, of course, it's our project, so that is a discussion I have to have with the CSC if we really expand a lot, but there has been interest to implement also in other countries quite a lot. So, but it depends how much can we get from CSC resources for this. So I think that's the only limiting thing. Of course, the data, there's quite a lot of data, especially from the big facilities. So you have to have the live disk base quite a lot. It's not like a cryo-EM problem, but that's also something that we need.
Yeah. Okay, thanks very much.